soon.
Okay.
So I raised that, but nothing changed. So I was not able to answer that particular assignment.
Well, you can you have you put the query in a discussion forum.
I have already made a discussion forum. Where is that, ma'am?
You have an access to a discussion forum on your like NPTEL site, so you have to raise your doubts or any query related to your assignments on that only.
Excuse me, ma'am.
Yes.
Ma'am, the query raised by the candidates on the discussion board has not been replied for the past weeks, ma'am.
Okay.
The problem raised by the student should mail to the NPTEL office directly.
I think the part of the discussion forum and the ones who is running the assignments is not my job. So I can just convey your like message to them, but I'm not handling the assignment part. I'm only handling the doubt sessions. So I will convey your message to them. Maybe they can reply to you. You can put your message on the discussion forum, and maybe they will reply you.
Sure, ma'am. I'm doing that.
Okay.
Just in case you try to remind or something like that. I have tried 2 times, so I missed that. So I
Okay.
don't know how to.
Okay, I will refer this problem to the concerned person, and maybe he can respond to you. If you have mailed also, then he will respond you accordingly.
I guess the way I mail is not the problem. I can do through the discussion forum.
Okay, you can try
Still,
once. You can try once through discussion forum, and then maybe I will also talk to the concerned person.
Yeah, sure.
Okay.
Thanks, ma'am.
Okay. Okay. So, are the slides visible? So shall we start? Okay. Uh, so we have some questions this week related to your strengthening mechanisms. So we'll do first some MCQ based questions. So we have the first question that says, during age hardening, major contribution to increase in hardness in the stage 1 is due to coherent precipitates, fine precipitates, semi-coherent precipitates, or small interparticular spacing. You have to answer this question. So what could be the right answer for this? Like during age hardening, we are trying to increase the strength of the material. So you have to say which of the following is the parameter that is responsible for age hardening and for strengthening of the this material. So you can try to answer that.
I think the option C is the correct one.
During the stage 1 hardening, we mostly have the small interparticular spacing that is helping in your hardening process. because once you let the material to age, it will have coarser particles. So in your initial stages of hardening, age hardening, it is actually the small interparticular spacing that is responsible for hardness. After that, once you are allowing it to age, so the material will be heated to above certain temperature. So there will be increase in their, say for example, interparticular spacing. So during initial duration or during initial stages, it is a small interparticular spacing that is responsible for the hardness. Okay. The second question says, according to Hall-Pitch relationship, the grain size is dependent on yield strength is. So you know Hall-Pitch equation gives you how much yield stress will be required to apply if you know the grain size or you know the grain diameter actually, right? So you have some relationship like this, sigma naught plus k under root of, this is your actual equation for the Hall-Pitch equation. So you have to say how is it dependent on your yield strength. This is your yield strength and how diameter is dependent. So the right option will be C, I think, right?
B, right?
Right. Okay. So this is your relationship based on your Hall-Pitch equation. Okay. So this is a simple question. Now we have another question that says, ductile fracture usually have features like dimple features, cleavage, river markings, cup and cone feature.
Dimple and cup and cone feature both.
Right. So this cleavage does not occur in your ductile fracture, right? Because you have a plastic deformation. This happens only in your when you have a material which undergoes plastic deformation. Also, river markings are not a part of your normal ductile fracture. So you have to see dimples in your, whenever you go for a fracture, it undergoes a ductile fracture. You will be seeing dimples and you will be seeing cup and cone type of a feature on the sample. Then we have another question because we know there are different types of loading like mode 1, mode 2, mode 3. So you have to say mode 1 type of loading refers to what? Whether it is tensile, shear, tear or compressive.
Shearing mode.
Shearing mode. Right, this is the right option. Shearing mode is the right option. Then we have another question that says slip will occur at, or like you have to say in which plane will the slip actually occur. So it is will it occur at 45 degree to the applied principal stress along the slip system even though it is not making 45 with the principal stress along the slip system at 45 degree to the principal stress or perpendicular to the loading direction.
Option B.
Option B, yes, it is along the slip system, even though it is not, because you have to see what was your, you have done some questions related to your critical resolve shear stress. So even though it is not at a 45 degree to your tensile, but if it is along the slip system, that is a necessary condition for a slip to occur. So it is B, option B for this. So we have another question that says, brittle intergranular failure takes place due to grain boundary suppression at high temperature, crack propagation through crystallographic planes, crack propagation through grain boundary, or cavity coalescence.
Madam, crack propagation through grain boundaries.
Uh, Crack propagation through grain boundaries, right? Brittle, because this is a brittle fracture, right? So it is saying it is one point is brittle, another point is that it is intergranular. So that means it is occurring along the grains. It's not moving from one grain to another, but it is inside inter to the grains, in between the grains. Takes place due to crack propagation to grain boundary, that is right. And also, if you have a grain boundary separation at high temperature, this is also true, because you know that your failures are responsible on your temperature and also on your, like, how much loading you are doing, like how it will be propagating and the properties of the material. But it also depends on your temperature, right? So you can see that.
Ma'am, I have a question in these options then. Like, when would we have option B and option D as a failure mechanism? Would you please?
Cavity coalescence is mostly done in a ductile fracture. This is a ductile fracture where you have said that you have a microwires that coalesce together and then it results in a ductile fracture. So it is definitely along a ductile fracture. Similarly, if you have a crack propagation through crystallographic planes, so if you have typical crystallographic planes, then that will be mostly, I think it will be a brittle fracture, but it will not be an intergranular fracture. I'm not sure about the part B, but about D, it is ductile fracture.
Okay, thank you, ma'am.
Then we have another that says we have according to Griffith's theory of brittle fracture, the crack propagates when a material is loaded equal to its cohesive strength. Nominal stress is equal to cohesive strength. Small cracks are more critical than large cracks. Cracks propagate when surface energy of two surfaces is equal to potential energy released due to breaking of the bonds.
Option D,
Option.
last option, ma'am.
According to Griffith theory, the first option says that the crack propagates when the material is loaded equal to its cohesive strength. Obviously, this is not true because we have seen that it fractures when it is less than your cohesive strength because of your inherent defects present in the material. Then it says that the nominal stress is equal to cohesive strength at the crack tip. Well, at your crack tip, you don't have a nominal stress as equal to cohesive strength, but it is much larger than that. Then it is saying that small cracks are more critical than large cracks. So, what do you think about that? Are small cracks more important than the large cracks?
No, ma'am, large cracks are more susceptible.
Oh, yes, right. So, this is also not right. And then we have another option that says the crack propagates when surface energy of two surfaces is equal to the potential energy released due to the breaking. So you have a net conservation of your energy. Anything energy that you are giving for deformation, that is being converted into creation of new surfaces due to breaking of the bonds. There is a net conservation of your energy in the material. So this is your right answer. So next question is how many active slips. This is something that you have to like remember. So you have like three slip systems in your HCP. So this is something you can skip. Then we have this numerical question that says you have to do this. So it says a long strip of polymer 1 centimeter wide and 1 mm thick with no cracks is subjected to a tensile force of 100 Newton along its length. So you have a material, its width and thickness is given and it is not having any cracks, right? And you are given a tensile load of 100 newtons. Now you are saying that after this tensile load, you are producing a strain of 0.3% in the material, and then you are given another stress, which is very identical to the initial polymer, but it is having some crack in it, and that crack is of length 1 mm perpendicular to its long axis at the center. So we have two cases: case 1 without defect, case 2 with defect. If the free energy is, so I'll just go like this. If you so this says if the free energy per unit area of the surface is 1500, estimate the tensile load necessary to break the second strip. So you just have to calculate if it was the first one was subjected to 100 Newton of a force and it is producing some strain. So you know about the conditions in the first case. Now in the second case, you are having your surface energy 1500 because you have now a defect inside the material. So you have to calculate the tensile load for breaking the second strip. What will be the tensile load? So you have to calculate your sigma, right? What is the sigma force for breaking? So you can first try to attempt, then you can solve it. You can take 2 minutes to solve it. So have you tried to attempt it? So first we'll see what we can get from the uh, questions, right? So we are given, we have a polymeric strip, right? So we can have some polymeric strip like this, and we are given the like for example, we are given the width, which is 1 centimeter, and we have given the thickness, right, of the material. So we can use in our first case sigma is equal to force per unit area, right? So we can use also, because we have been given the strain, so we can use the stress strain equation, that is something like this. So you know your value of sigma you have to find here. So from the first part, we know the force that is being applied, we know the strain, we know the area that on which it is applying. So we can see this is your area. So this is your strip of polymer, right? So we have to take the area will be the length into breadth, right? This will be, it can be something like this, right? So we are given the area of this polymeric strip, right? So we can calculate our this Young's modulus. First we will try to find the property of the material, which is this Young's modulus. So that will be given by your sigma, that is equal to force by area, right? And it will be divided by your strain. So you know what is the force that is being applied in case 1, that is 100. You know the area. So your area given 1 centimeter and 1 mm. So you have to convert it to meter, because we have newtons. Yes, we can convert it to meters. So it will be around I think 10 to the power 3 and 2. So it will be -5, right? And we have some strain in the material, that is 0.3. So 0.3 means it means 0.3 multiplied by 10 to the power 2. 10 to the power -2, right here. Okay. So you can calculate the value of your Young's modulus. What is the value of your Young's modulus? We have just put the value in the equation. Do we have any answer for the Young's modulus?
Ma'am, I have got 3.3 10 raised to power 9 Newton per mm, Newton per meter square.
3.33. I'll just write it.
Into 10 raised to power 9 Pascal.
9.
Or Newton per meter.
9. Okay.
Yeah.
Okay. So this is your E. That is your Young's modulus. Now in your case second, we have to find actually the load that needs to be applied with a crack. So in our case 2, we know according to the Griffiths theory what is the load relationship between your load and your crack. For example, properties of your crack. So it is something like 4 gamma E divided by, I think it is pi C. So this is your Griffiths equation. So you know the value of your gamma, that is just nothing but your surface energy. So if you are given the free energy per unit area of the surface is this, that is given 1500. Your Young's modulus you are also given. This is something that you have found out from the first case. That was the property of the material that you had to find. You know the pi. Now you know the C. So this is your crack length. So what is the crack length in this case?
1.5 mm.
It is having 1 mm as a crack, so you have to find your it has a crack length of 1 mm perpendicular to its long axis, right? So you have to find the tensile load necessary to break the second strip. So you have to find the load. So you can calculate the value.
Ma'am, I have a query in this question. Why can't we calculate this stress to break the strip when we have a crack using this formula? Sigma max is equal to 2 into sigma nominal under root C by rho.
That is your I'm not getting what is the formula.
Reference theory,
Yes,
it says that sigma maximum is equal to 2 times sigma nominal multiplied by under root C by rho.
Okay.
So sigma max we can calculate when we have sigma nominal. Sigma nominal is equal to load divided by the area of resistance W into dt.
Yes.
So in this case we do not require the value of strain if we apply this formula.
But you do not know the value of your curvature, right? I think in your formula which you are saying, you might be needing the curvature of your this crack, right?
Yes.
So yeah, if you have a question like that where you are given the curvature, then that you can decide based on that also.
Ma'am, how do we know this is internal crack or a surface crack?
Yes, in this question it is not given. I think it is not given. Perpendicular to its long axis yeah, it is given because it is given at its center. It has a crack of length 1 mm perpendicular to its long axis at its center. So you'll be given if whether it is.
The center word has been referred to axis only. It is not like that it is made of pieces.
No, it is given that it has a crack of length 1 mm perpendicular to its long axis at its center.
Okay, that means at the middle of the strip.
Yes.
Okay.
Yes. Okay, so we'll do next question.
Ma'am, would you please check the answer?
What is the right answer?
I have got 1.12 into 10 raised to power 8 Newton per meter square.
I think it should be out of these options only. if you have got any of the options. I am
Yes,
also
ma'am.
not sure of the answer, but it will be one of these options. Have you got any option from the this?
No, ma'am.
So what have you taken the crack length as 1?
I have taken 0.5, ma'am.
Okay, so can you use 1 mm as your crack length and then see if you have got the answer? I think it is because it is not
Yeah.
along the perpend. It is, you have to see what is the crack.
Okay, madam, I will read the problem.
Yes, yes. So okay, we can move to next question. For that, we have uh, a question which says which of the following isn't a strengthening mechanism for multiphase metals? So multiphase element, you have a multiphase material which is having say alpha beta phases, and you have to say which of the following will not be a part of your strengthening mechanism. So you have precipitation strengthening, dispersion strengthening, solid solution strengthening, or Martensite strengthening.
I think D is the right answer.
See, first we have precipitation strengthening. Precipitation strengthening only occurs when you have some precipitates forming in the material, and it is only possible when you have some another element or another phase in the material, right? You have two phase systems. So you have one of the elements, say alpha and beta. Once you are allowing the precipitates of something to form, because in precipitation strengthening you always follow the Solvus line, right? This is something that you follow. Initially you are in this region, then once you quench the material, you allow the precipitates to form, and that results in the precipitation strengthening. So you always have a multiphase in this. In dispersion strengthening also, because you have a dispersion of some element, right? So you always need a multiphase system in this, because you need you have a base matrix and you have dispersion of B atoms inside the A atoms. So these will be required for dispersion strengthening. And for solid solution strengthening, it is only occurring when you have a single phase. If you have seen solid solution strengthening, you always need to have a single phase for the material, while for this Martensite strengthening also multiple phases are required. That is why you undergo, for example, you have a material steel and then you have two phases. First you have a gamma phase, but once you quench it, you you have a formation of another phase which is like cementite. You have two phases, alpha and beta phases. So you are allowing the cementite phase to help you in strengthening of the martensite, right? So you have to see if you have how many phases are responsible. For solid solution, you only have one phase that is responsible, while for others, you always require another phase for strengthening mechanism. Then we have another question that says which of the following is not improved by grain size reduction? You know that your grain size, if you are reducing the grain size, there is some improvement in your material. Like for example, you have a better strength in a material, you have more resistance to your dislocations. So if you are reducing the grain size, which of the following will not be affected or will not be improved, right? So you have hardness, toughness, elasticity, and strength. So obviously, because we are increasing the grain size, sorry, we are decreasing the grain size, so we are always strengthening it. Whenever you have a finer coarse size, finer material, it will be having more strength as compared to your coarser material, because it has more resistance to dislocations, it has more grain boundary areas, more dislocation piling up, so it will be having more strength. So this is right, but we have to say which of these is not improved out of the other three options.
Elasticity.
Right, because elasticity is the inverse function of your strength. So obviously hardness is increased if you have a grain size reduction. Toughness is also increased, but your elasticity is not improved if you are reducing the grain size. So elasticity is the right option. Then we have another question that says in strain hardening, the body is plastically deformed. True or false? So you know we have different types of deformations. You have elastic deformations, plastic deformations. So you have to say in your strain hardening where you are strengthening the material. So is the body plastically deforming or it is not?
Plastically.
Yes, this is the right option. The plastically it is deforming, so it is true. True. The option is true. Okay, so we have another question that says the strain hardening will be more effective in fine grain size metal, coarse grain size metal, fine grain size metal with solute atom, coarse grain size metal with solute atom.
But option C, I think, is the correct answer.
Right. So what happens if you have a strain hardening, if you have a fine grain size metal, it will be effective. It is no doubt. But you have to say out of the four options, right? Fine grain will also have a strain hardening effect. Coarse grain will not have as much as you have a fine grain. So this will not have. Then we have fine grain size metal with solute atom. Obviously, if you have a fine grain, you are strengthening it by grain boundary also. You are also strengthening with your, say for example, solute, you have precipitates formed or you have dispersion of the atom. So this also affects your strain hardening, improves your strain hardening. Then we have coarse grains with solute atoms. So this is not the right option, right? Because it's a coarse grain size. So overall fine grain size is important for your strain hardening, and also if you have some dispersions or strengthening mechanisms, so they will overall improve your strength. Then we have another question that says according to Hall-Pitch equation, Hall-Pitch equation, the correct relationship between the grain diameter and yield strength will be which of the following. So you know what is your Hall-Pitch equation. So I'll just write it here first. So you have to say how are they related, yield strength and your diameter. Which of the following graphs is the correct representation for the two? Because you have some x-axis which is a yield strength, you have y-axis which is grain diameter.
The first one is the correct answer.
Right. Why we have the first one as the right option? Because you know this is a variation of yield strength with your diameter. So you know there is some exponential change, right? The exponential decay of your yield strength with the grain diameter, as it is seen from the equation, because we have delta, sorry, sigma y is affected by diameter, which is 1 by 2 raised to power 1 by 2. So this is the exponential decay of your yield strength with the grain diameter. So this is the right option. But if it would have been here, the scale would have been 1 by d. Like you already have a scale of 1 by under root of d, then the slope will be a straight line, right? So you have to see what are the scales of your graph, whether it is yield strength versus only grain diameter, or it is also some exponential function with it. So overall the graph A is the right option. Then we have another equation. This is the graph that you will have if you have a yield strength changing with your diameter, right? So you have a straight line because you have now a linear plot between the two. So we have now a question that says from the plot of yield strength versus grain diameter for a 70-30 cartridge brass, determine the value of yield strength Ky in the Hall-Pitch equation. Predict the yield strength for this alloy when average grain diameter is 1 into 10 to the power minus 3. So you have to first find out the constants in your Hall-Pitch equation. So you know your Hall-Pitch equation has some constants. Say for example, this is sigma naught plus k by root d. So this is your linear plot which is given here. You are given a yield strength versus diameter. So this is your y is equal to mx plus c. This is your standard equation for a straight line. Y is sigma y, which is your yield strength. Your m is the slope for the equation, which is this, right? K. Your sigma naught is your c, right? So you are given the straight line with the intercept of c. So this is your overall equation. Now you have to find the yield strength of this alloy when the average grain diameter is this. So you are given the diameter, okay? You have to find this, but you do not have these values yet, which is sigma naught and which is k. So you have to find these two values from the graph, right? So you are given a plot, you understand that this k can be found from the slope of the graph and the sigma naught can be found from the intercept of the graph, right? So if you can try to find m and sigma naught from the graph, then the equation is solved. The question can, then you can plug in the values and get the value of our yield strength, right? So can you calculate the value of m, which is the slope, from the graph? Because it is simple, you have to calculate the slope. Slope is nothing, it is just a when you go for simple mathematics, slope is nothing but it is the difference between the 2 points along the y-axis and along the x-axis, right? So you can choose any 2 points on the graph and you can choose the slope. So you can try to solve this, then we can solve it again. Okay, it comes out to be 13. So you are saying it is around 13 MPa, right? I think MPa, yes, 13 MPa. So this is your value for K. So what is the value of your sigma naught now?
Around 25
Okay, around 25.
megapascal.
Okay. So now you can solve this question which says the predict the yield strength of the alloy when average diameter is given. So you just have to now put the values in the equation. So that will be your sigma y, which you have to find, that is equal to your 25 that is given plus 13 as per you. So and then we have diameter, which is given to be 1 into 10 to the power minus 3, but we have to convert it to I think mm is given everything. No, we have to calculate it, convert it to meters, right? This is in mm. So you can calculate what is your sigma y. So can you try to calculate the value of your sigma yield strength? If you also see from the graph, you are actually in this region 0 to 4, so this will be simply 2, so you are here around, so your yield strength should be less than 50. I think no, yes, we are in 10 to the power minus 3. No, you're not in this region. I think we are in the region of, what is the right answer that you are getting? I think there is some. What is the right answer? We are somewhere around here because we have 5 to the power minus 3 somewhere here, right? We have the value here somewhere in grain diameter 5 into 10 to the power minus 3, so it will be above 200. Your value of your yield strength will be above 200. because you see you have decreased the part this grain diameter. Your grain diameter is decreased in this equation. So have you calculated?
No, I'm not getting the correct answer. I'm getting 400 plus.
Yeah, that is fine. You are getting around about 200. So it
No,
will.
ma'am, I'm getting 400,
Yeah,
more
that.
than 400.
Yeah, that is fine.
But madam, if the 400 is the correct answer, then we are going beyond this graph area, ma'am.
Yeah, that is fine. That is what I am saying, that it is beyond this graph. That it is
How,
about
ma'am?
so anywhere about 200. This if you extend
But
this.
ma'am, if we try to solve this problem by graph itself,
Mm-hmm.
say the average grain size is 1 into 10 raised to power minus 3. So
Mm-hmm.
if we take the if we take this value 10 raised to power minus 3,
Yes, this is your value. 10 to the power
okay.
minus 3. Somewhere to this side.
No, ma'am, the graph has been plotted as 1 of the under root d, not in terms of d.
But at the top scale, it is given in DMM. You can see.
Okay, ma'am.
You can see this scale
Ma'am,
per.
yeah,
Yeah.
I'm getting 436
Okay. Okay, that will be the answer. I think 436
Yeah.
megapascal will be the answer, because according to the uh, graph also, because you are decreasing your grain size, so your yield strength should increase. That is what we want to say, right?
Yes, yes, ma'am.
So then it should be the right answer. Okay, so next question says that we have a material with grain size of ASTM number 6 and has a lattice frictional stress of 100 meganewton per meter square and locking parameter of 0.1. So you have to say what is the grain size of the material and what is the yield strength of the material. Again, you are given some problems related to your lattice frictional stress, which you know, which is according to the Hall-Pitch equation sigma naught, right? This is your given, and then you have a locking parameter, which is K in the Hall-Pitch equation, right? Now you have to find the grain size of the material. So if we use the equation that says the yield strength is dependent, again using the same equation, is dependent on your frictional constants and your locking parameter and your diameter of the grain. So you have to say so you can find the yield strength if you know all the parameters, you know this K value. You have to see what is the value of this D. This is your grain diameter, but in your question you are given a grain size of ASTM number 6, right? So you should know that if you have a grain size of ASTM some number, you have to convert it into say grain diameter, right? So you have to make this conversion and then only you can use this formula to find the yield strength. So according to ASTM, so you know according to ASTM you have a relationship between your number of grains and your ASTM number. So it is something like this. I think this is something that we have covered in earlier classes. So it is related to your 2n minus 1, right? Something like this. And this n is your ASTM grain size number. And this n is your number of grains per square inch, right? Per square area, mostly we say, but per square inch. So this is, there is no value for the magnification. So for example, if we take the magnification as 1x, right? For the calculating the parameters. So if we put the value of magnification, we know the value of ASTM, which is 6. We can calculate the number of grains per square inch in a material, right? So you can put the values and you can calculate n first. First we'll calculate the number of grains. So that will be 2, 6 minus 1. So this will be 5 multiplied by 100 multiplied by 100, right? So this is 32, I think 32 into 10 to the power 4. This is your n, the value of your number of grains. So this is your number of grains per inch square. Okay. Now, okay, so because we have to find the grain diameter, so this grain diameter is mostly in your mm or your meter square. So we can first convert this into square. So can you convert what is the value for this? What is the conversion for inch to So you have to convert it in square.
Around 500.
Okay, 500 is around. Okay, so I will write 500 here. So that is your 500 per square, right?
Yes, ma'am.
Okay. So your now value of your n is given, which is the number of grains per square per square millimeter, right? Now we still have to find this d, which is the grain diameter. So this grain diameter is given by the equation where we have the number of grains, which is equal to 1 divided by or we can say first we can calculate this. This is actually under root of number of grains is equal to 1 by d, right? So this is your number of grains, how many number of grains are there, and the diameter of the grains. Obviously if you have more number of grains, that means the diameter is a finer size, while as if you have a larger number of grains and smaller number of grains, then you have a coarser structure representing the number of grains and your diameter. So you can calculate the value of d from here. So you can see what is the value of your grain diameter. Because this is square, so units will be finally because you're under root of the value will be under root of n. This is a simple formula because you know square means it is the area, but you want to find a diameter. You want to go from 2d to 1d. So you may take the under root of that value, but you know if there is a larger number of grains, it is having a smaller diameter. So you take the inverse of that. So that will be your diameter. So you can find what is the diameter.
0.0447.
That will be in right?
0.447 millimeter.
Something like this.
0.044.
Okay. Is it okay? Okay, so now you have the value of your d, you have the value of your sigma naught, you have the value of k. This was something that you have to find. The question wanted to, in this question we actually wanted to know if you have given a ASTM size number, how will we convert into grain diameter. So this will be important. So you have calculated the d, now you just put in the values and find the value of your sigma, which is your yield stress.
I have got 100.476.
100
476.
147 you mean?
Yeah. 100.476.
Okay.
Newton per meter square.
Okay, so that is your values are this is Newton, right? Or mn?
Meganewton per meter square.
Yes, yes. So that is your answer, right? So you can calculate the STM grain size number, and then from that you can find the value of your grain diameter. I think that is all for today. If you have any questions.
Would you explain the meaning of this sigma zero lattice frictional stress?
This lattice frictional stress is nothing but it is the like for Hall-Page equations, we always are calculating what is the change in your yield stress with the change in your diameter, right? But this there is always a minimal stress that is required because the yielding is a phenomenon that occurs because of your dislocations, right? So you have actually a dislocation phenomenon occurring in the material because of your grain diameter, because of your, say for example, grain boundaries, or because of your size of the material. But you always have to initiate the dislocation motion, and that dislocation is your minimal stress that you have to apply on the material for a dislocation to initiate its movement. Once it is initiated, then you have to see the yielding will occur only if you are continuing that amount of load. So it is actually the property of a lattice, how your atomic arrangements are taking place inside the material. Based on that, you always have to give some extra stress, and on top of that stress, then you will be giving this amount of stress. Because if you see, this is actually equation, the stress, complete yield stress, is actually a function of two stresses. This is one, this is two. So your two stress, you are actually having two forces that you are adding here. So this is your minimal force that is required, and on top of that your geometrical factors that are coming into place because of your precipitates, grain boundaries, everything. So this is your another stress. So you have to sum the two stresses to find the overall yielding of the material at which it will take place. So it is just a balancing of your forces.
Like we have heard about initial friction in mechanics.
Yes, similar to that. Yes.
Analogy to it.
Yes, similar to that. Right.
Okay.
Okay. I think that will be all for today.